Hello everyone, welcome to my channel. So in the last video, we tried to predict gold price using dynamic linear model or DLM. Recall that dynamic linear model is a specialized case of state space models which look at time series data in two hierarchies. The first one is the observational level and the second one is the system level. Each level has its own variance. So, in the last video, we assumed that we know the values of those variances, but in real life, it's very common that we don't know actually. We just have no clue. So, in this video, we're going to relax this assumption and estimate them first before using the estimated variance and to build our model and generate forecasts. So, without further ado, let's get started. So first things first, let's load our packages. The first one is DLM. This package is for estimating the variances and implementing dynamic linear model. And then deployer is for pre-processing data, and ggplot and plotly are for visualization. Okay, now let's go to the data. The data is still the same as in the last video. It's 1 year data and it's downloaded from NASDAQ. Here's the link. And then the data available now is from June 27, 2022 to June 23rd, 2023. The two lines here, later, are for pre-processing the data. So this line here is for converting the class date from factor to date, and then this line here is for sorting the dataset in ascending order. You can check out the previous video to hear further explanation about it. Okay, so let's run these. Okay, so this is the clean data. We have 250 rows, or you can also see it here. 250 rows or 250 days instead of 365 days, like one full year. We only have 250 days because our gold price data only available for business days. So it will exclude weekends and US holidays. Now let's visualize our time series. This code block here is for making the time plot. We're going to denote the high prices using blue line and the low prices using orange red line. And then geom ribbon is for shading the differences between the high price and low price. The price is in USD, so that's why the y-axis is USD. It looks exactly the same as in the last video. I didn't change anything. See, it's June 2022 to the end of June, almost the end of June 2023. Now, the next thing we should do is to build our model. But we need variance values to put into our models. So we would first apply MLE, maximum likelihood estimation, to estimate the variances. Note that we want to estimate the variances separately. So we're going to have 4 variances. So 2 are for the high price and 2 are for the low price. Or if you want to divide it by level, 2 variances are the observational level variances, and the other 2 are the system level variance. Now let's talk about maximum likelihood estimation. So let's say that we have our time series and the data point at each timestamp in our time series is our observation YT. And given this data, we want to predict its variance, V. So it could be denoted this way, V given YT. although the more common notation is this, theta given yt. Now, we don't know the value of this notation, but we can write down the reverse of it. So, yt given theta. Or maybe we shouldn't have written this. We shouldn't have written this. Just y. Given a certain value of theta here, the joint probability density of y is the probability of y1 given theta times the probability of y2 given theta, and keep going like that until the probability of yt given theta. In short, we could write it as the product of probability of each y. The product of each probability given theta. So I is starting from 1 until t. And sometimes we also write this as the probability of y1, y2 up until yt given theta. So y1, y2, and each of the y value are the realization of a random variable. So what is the probability that y1 is exactly that value, a, for example, and so on. This line here is very related to likelihood, because likelihood up to a constant value is defined to be this probability density function I've just mentioned. So more formally, we can write it as like this. L is for likelihood, and likelihood is a function of theta, and constant times this. Just paste it here. Now, in order to calculate the likelihood, we need theta, right? Because likelihood is a function of theta. But we don't know the value of theta yet. And we want to find it such that the likelihood would be maximized. This likelihood value would be maximized. More technically, we want to find a value which can make the first derivative of the likelihood equals 0. Now, finding the first derivative of product of functions, this product of functions is really hard. So to make it far more manageable, we're going to take the first derivative of the log likelihood. The log likelihood would look like this. This is the log of likelihood. And because we're taking the logarithm of product, we get summation. Like this. And we want to find the first derivative of this. This. To find the theta we want. But before that, we still need to determine the probability density function of each data or each observation. So you probably know it as the marginal density function. This is quite easy though, since we're dealing with DLM, which assumes the distributions of all the observations, state factors, parameters, and variances to be Gaussian. So the probability density function here, I'll write it here though, P of the probability of y given theta. Since this is Gaussian, so it would be normal with mean mu and variance sigma squared. So 2 pi this is a mu. Okay, this is mu. And So the log likelihood could be written as this. So we're taking the log of this actually. It would be written as this. This apostrophe here is not power. It's not of power 1, but it's to denote this factor here to be transposed. Okay, and this is what we want to maximize here. Note that mu here is the mean of our time series, which will be assumed to be known. And then sigma square is the variance we want to estimate. In finding an estimate for the variance, though, we can also use the Bayesian matrix, which is the second derivative of our log likelihood function, to get the variance of our estimated sigma square. So the estimated variance, the variance of our estimated variance. I hope that's not confusing. But we won't look at it for now. We won't look at it in the programming. In R, there are 2 steps to apply MLE to get our variances. Firstly, we define a function. So let's go here. So firstly, we define a function which could return a model. When we build a model in the function, we would put, what I mean by building the model is this. So in the function called build, we will build our model. And when we build a model in the function, we would put parameters of the function as our variances. So here, we name our function as build. And we are putting a parameter, which is a vector we will call parm. Each component of parm would be used as a value of a variance. So for instance, the first component of parm here would be used as the observational level variance V of polynomial model. And then the second component of parm is used as the first entry of the diagonal of the system level variance W of polynomial model, and so on. Because we want to estimate the variance here, so that's why we are putting our function parameter. And so on until 5 here. In this case, it's until 5. Okay. Secondly, we put our function from the first step into DLM-MLE. So if you see here, DLM-MLE function, and one of the parameters or one of the inputs that we're using is build function here. So what happens under the hood is that DLM-MLE function would call optim, which is a built-in function in R for optimization. Optim would automatically pick some random values of theta and then use DLM-LL for evaluating the log likelihood. So LL here is for log likelihood. And the theta, which maximizes the log likelihood would be returned by the optim function. It's gonna be our variances. This vector of zeros here is a vector which has the same length as parm. So parm in this case has the length of 5, so that's why we put 5 here as well. It's a vector of initial values of the variances. For simplicity, we set all of the variances we want to estimate to be 0. So there you have it. Okay, so now let's run this part. Our estimated variance would be stored in bar. This is bar. In addition to the estimated variance, DLM-MLE would also return other values such as convergence. If the value of convergence is larger than 0, it means DLM-MLE has not reached optimum yet. This might take a while. Okay, now it's done. Let's see the convergence. Let's check it. Okay, so we see that the convergence for both fittings are 0. So, meaning that MLE has reached optimum when finding the most appropriate variances for our time series. So I'm going to denote the variances for the high price time series with fit high, and the other one with fit low. Okay, now that we've got our variances, we can put them back to our build function. So recall the build function here returns a model, right? Because inside the build function, we are defining our model, which is the addition or the superposition of polynomial model and seasonal model. And we didn't know the value of barm earlier, so we could only put it as an input for DLM-MLE. But since now we know, we can call build function and get our model. So the parameter that we needed earlier is going to be put here. Okay, let's run it. And here is our model. Here is our high price model until here. Okay, so we can see that the estimated variance for the high price is 0.0017. This is much smaller, by the way, than the last video. So in the last video, we assumed the observational level variance to be 1. But after estimating based on the data in the high price time series, it's estimated to be this. And then the W value, the first diagonal here, is 225.399. That's way larger than our assumed earlier, which is only 2. Okay, so that's for the high price. And let's look at the model for the low price now. The variance here is 2.43. So the observational level for the low price is estimated to be higher than the one for the high price here. And it's larger than our last time variance as well. Anyway, and then for the W, it's 216.7621. And then the other one, like this, the variance for the seasonal level is really small. It's really close to 0. And it's roughly the same for the high price as well. Here. Okay, now that we've got our model, we can finally do filtering and forecasting. Filtering is the process of updating our inference about the state vector and one step ahead forecast. Using the package DLM in R, we can filter with DLM filter function. DLM filter function And the arguments are the time series and our model. The output returned by the filtering process would be used to generate our forecasts. So that's why for the LM forecast function, we will take the output, which is filtered high, as an input. So we do filtering on the high price now. And this is going to be our forecast, 1950.819. And then, yeah, let's do the same for the other one, for the low price. And, oh yeah, by the way, the forecasted value is stored in F, in the component F of the output of the LM forecast, which is in this case, we name it as forecast low or forecast high, depending on the time series where we are forecasting. Okay, so to look at both prices forecasted. So the high price is forecasted to be 1950, while the low price is estimated to be 1913. Okay, and so this code, okay, the next two code blocks are for visualizing our data and forecasts. Okay, so let's look at the high price first. We predicted earlier that the data would be 1950. So it's a little bit higher than the data. The data is 1949 and the predicted for the next day is 1950. And then this is for the low price. And for the low price, we predicted to be slightly going down from 1919 to 1913, slightly decreasing. Okay, but if you take a look at it, actually the filtered level is kind of a little bit more accurate than the last time. Okay. Here. But let's see what the real data says. So imagine that we're still in June 25th of 2023, and then we want to predict the high price and the low price on June 26th. So, yeah, after getting our prediction, which is 1950 and 1913, now let's see the real data. So here is the data. June 26, 2023. The high price is 1943, actually, not 1950. And actually, the high price is going down instead of going up as we predicted. And then for the low price, it's actually going up from 1919 to 1931, but we predicted to be going down from 1919 to 1913. So yeah, in this case, getting an estimate using MLE doesn't improve our estimation, doesn't improve our forecast. Maybe we need a better or more complex models to get a better and more accurate forecast, or we can also maybe use another technique to estimate our variance. There are two popular techniques to estimate it actually. This is the first one, MLE, and the second one is based on the Bayesian statistics, so keep sampling. Keep sampling would be very useful, especially if the distribution of our data is not normal. Okay, so that's it for today's video. All the codes that I just presented here is available on my GitHub, would be available on my GitHub by the time this video is uploaded. Thanks so much for watching, and yeah, please consider subscribing to my channel, TimeSeries. See you next time. Bye-bye.